Welcome to today's paper reading. Today's paper is titled, Weighted Ensemble Models Are Strong Continual Learners. This paper was published on AR14 by Imad, Eddine, Marouf and colleagues from Telecom Paris and University of Trento. In this work, the problem of continual learning, CL, is studied, where the goal is to learn a model on a sequence of tasks with the assumption that data from previous tasks becomes unavailable while learning on the current task data. Continual learning involves balancing between learning on the new task, which is referred to as plasticity, and maintaining performance on previously learned concepts, known as stability. To address this stability-plasticity trade-off, the authors propose a method called Continual Model Averaging, CoMA, which performs weight-ensembling of the model parameters from previous and current tasks. This method achieves high accuracy on the current task by leveraging plasticity while ensuring stability by not deviating too far from the previous weight configuration. An improved variant, Continual Fisher-Weighted Model Averaging, CoMA, is also proposed, which selectively weighs each parameter in the weight ensemble using the Fisher information of the model weights. Both CoMA and CoMA are conceptually simple, easy to implement, and effective in achieving state-of-the-art performance on several standard continual learning benchmarks. Continual learning, CL, faces significant challenges, primarily catastrophic forgetting, which leads to a decline in performance on previously learned tasks. Pre-trained models, PTMs, such as vision transformers, VIT, have been shown to facilitate incremental learning due to their strong initial representations. To address these challenges, the authors propose several solutions, including weight averaging, WA, continual model averaging, CoMA, and continual Fisher-weighted model averaging, CoMA, which aim to balance the stability-plasticity trade-off in CL. Figure 1 compares existing model averaging techniques with our proposed technique for continual learning, CL. In part A, averaging the weights of the pre-trained model and the one fine-tuned leads to simultaneous improvement in out-of-distribution and target dataset performance. Part B shows that Model SUPS combines multiple fine-tuned models, resulting in a robust unified model. In our proposed technique, Part C, CoMA weights the current and past models' weights based on their Fisher information matrices, represented by F, achieving balanced performance for both current and old tasks. In the realm of continual learning, CL, various strategies have been employed to mitigate the issue of catastrophic forgetting. These include regularization-based approaches that stabilize parameter changes, replay-based methods that regenerate past data distributions, and architecture-based techniques that allocate specific parameter subspaces for each task. More recently, the use of pre-trained models, PTMs, has shown significant promise, with techniques like prompt-based learning and sequential fine-tuning outperforming traditional CL methods. Additionally, ensemble methods, both in output space and weight space, have been explored to enhance model performance and computational efficiency. These methods, including linear model connectivity, provide a robust framework for understanding and improving CL. The classification model M-Phi consists of a feature extractor F and a classification head H, both parameterized by a unified set of parameters phi. The feature extractor is initialized with parameters theta 0 of a pre-trained model, PTM, and is then sequentially trained on a series of incremental tasks, each represented by the corresponding training set dt, for t is an element of 1, t. The primary objective is to achieve robust performance across the test sets associated with these tasks. Specifically, for each task t, the dataset dt is defined, and CT denotes the set of novel classes introduced in task t. In class incremental learning, CIL, evaluation is conducted across all the observed classes without the need for task index labels. Figure 2 illustrates the parameter trajectory with model averaging in the loss landscape. In Part A, the trajectory shows models being reinitialized at the start of each task, leading to disparate solutions. This approach can result in models that are not well suited for all tasks due to the significant differences in their parameter spaces. Part B depicts a scenario where a decreasing lambda equals 1/t is used for uniform averaging without reinitialization. This method shows the convergence of model parameters towards a solution that balances between tasks, ensuring that the model retains knowledge from all tasks. Finally, Part C illustrates a non-uniform averaging approach where recent tasks are given more weight. This results in a solution that remains close to the latest tasks model while still considering previous tasks, thereby maintaining a balance between adapting to new tasks and retaining old knowledge. The experiments were conducted on 4 CIL benchmarks: CIFAR 100, ImageNet-R, CUB 200, and CARS 196. CIFAR 100 contains 100 classes of natural images, each with 500 training images. ImageNet-R includes images from 200 classes, divided into 24,000 for training and 6,000 for testing. CUB 200 consists of images from 200 bird classes, with about 60 images per class, half for training and half for testing. The metrics used to evaluate the performance are the average classification accuracy of all the classes ever seen after learning each incremental task, (INCACC), and the accuracy after learning the last task, last ACC. The results show that CoMA consistently outperforms the best-performing CIL baselines, SLCA and RANPAC, across all benchmarks. CoFIMA, the improved variant of CoMA, shows even further performance improvement, achieving new state-of-the-art results in CIL. This highlights the benefits of adaptive model averaging based on the importance of the parameters for a given task. Figure 3 illustrates the performance enhancement of CoFIMA across various pre-trained models, PTMs, on the CIFAR 100 dataset. CoFIMA consistently improves upon the baseline SLCA method. For example, with the VT-Tiny backbone, CoFIMA boosts the last accuracy from 80.25% to 82.96%. Similarly, with the VTB/16 SAM backbone, CoFIMA achieves an accuracy of 90.48%, demonstrating its effectiveness in both supervised and self-supervised learning contexts. This figure highlights CoFIMA's versatility and its ability to enhance performance with different backbones. Figure 4 presents an ablation study on the effect of lambda, a parameter used to balance the stability/plasticity of the model during averaging, on the CIFAR 100 dataset. The study highlights that CoFIMA demonstrates superior performance compared to YSEFTCL across various lambda settings. Notably, the best performance is achieved with lambda equals 0.3, indicated by the red marker point. This optimal setting provides the best trade-off between learning new task T, plasticity, and preserving knowledge from previous tasks, stability. The results underscore CoFIMA's effectiveness in incorporating new knowledge while preserving old information, maintaining a critical balance in continual learning scenarios. Table 1 presents a comprehensive comparison of state-of-the-art continual learning, CIL, methods on 4 benchmarks: CUB 200, CARS 196, CIFAR 100, and ImageNet-R. The methods are evaluated using the VTB/16 backbone model, which was supervisedly pre-trained on ImageNet 21K. The table highlights that our proposed CoMA method consistently outperforms the best-performing CIL baselines, SLCA and RANPAC, across all datasets. Additionally, the improved variant of CoMA, CoFIMA, demonstrates even further performance enhancements. This comparison underscores the effectiveness of model averaging in CIL and the superior performance of our methods in handling incremental learning tasks. Table 2 presents a state-of-the-art comparison of various continual learning, CL, methods using a vision transformer, VTB/16, backbone pre-trained with self-supervised learning, MoCo V3, on ImageNet 1K. The table highlights the performance of CoMA and its improved variant, CoFIMA, across different benchmarks including CUB 200, CARS 196, CIFAR 100, and ImageNet-R. Key metrics reported are the average classification accuracy of all classes ever seen after learning each incremental task, INCACC, and the accuracy after learning the last task, last ACC. CoFIMA consistently outperforms the state-of-the-art methods, demonstrating significant improvements in accuracy across all datasets. Notably, on CUB 200, CoFIMA achieves a last ACC of 77.65% and an INCACC of 83.54%, surpassing the performance of SLCA. This trend of superior performance is also observed in CARS 196, CIFAR 100, and ImageNet-R, showcasing CoFIMA's effectiveness in balancing the retention of old knowledge with the acquisition of new information. The results indicate that CoFIMA is highly effective in approaching the upper bounds of CL performance, even when using a self-supervised pre-trained model. Table 3 presents a detailed comparison of our proposed methods, CoMA and CoFIMA, against various weight averaging baselines using a supervised pre-trained model, VITB/16. The results indicate that CoFIMA consistently achieves superior performance across all evaluated datasets, including CUB 200, CARS 196, CIFAR 100, and ImageNet-R. Notably, the weight-ensemble approach, when initialized with the previous task parameters, theta t-1, shows competitive results in CIFAR 100 with a last ACC of 91.69%, but it underperforms in datasets like CARS 196, achieving a last ACC of 71.82%. The exponential moving average, EMA, technique, while consistent, generally yields lower performance compared to CoFIMA. This table underscores the effectiveness of CoFIMA in balancing the retention of old knowledge with the acquisition of new information, thereby approaching the upper bounds of continual learning performance. In this study, the authors introduced CoFIMA, the first method to use weight averaging techniques to address catastrophic forgetting in continual learning. CoFIMA is built on two main principles: model averaging to balance prior and new knowledge, and the incorporation of Fisher information to weight parameters intelligently. This approach effectively reduces catastrophic forgetting by adjusting each parameter's value based on its importance. The benchmarking results show that CoFIMA consistently outperforms existing state-of-the-art methods across various pre-trained model backbones and datasets. The performance metrics highlight high last accuracy, competitive results compared to joint training, and strong performance against YSEFTCL. The authors would like to express their gratitude to Yasser Benigmim, Khalid Ublal, and Ekaterina Iakovleva for their valuable discussions and feedback on the draft. This research has been supported by the French National Research Agency, ANR, and funded by the European Union's Horizon Europe Research and Innovation Programme under Grant Agreement No. 1011202237, Elias. Additionally, the research was funded by the EU Project AI4 Trust, No. 1010709190. The research was also partially funded by the HI, Paris Center on Data Analytics and Artificial Intelligence. Access to the HPC resources of IDRIS was granted under the allocation AD 0110138660 made by GENSI. Thank you for watching.